Alright, so let's say given this diagram here of a collision between two masses A and B. The question says, consider the collision between two masses A and B above. Find the final velocity v2 for the collision. To start, we know the collision is a completely inelastic collision. But why? A completely inelastic collision is a collision in which the colliding objects stick together and move as one object after the collision. So we can see in the after scenario that these two masses are indeed moving in the same direction, stuck together. Some key attributes to help solve during an inelastic collision, two things are true. One, momentum is conserved, which means the total momentum before is equal to the total momentum after. And the second thing is the total kinetic energy is not conserved. So the total kinetic energy before is not equal to total kinetic energy after. The system loses kinetic energy during the collision. So if we apply this to our example, this is our example here, and we can use the conservation of momentum, which is that the total momentum before is going to be equal to the total momentum after. But what is the total momentum before and total momentum after? The total momentum is the sum of the individual momenta of the system. So we can say that the total momentum before is going to be the momentum of the A mass before plus momentum of the B mass before. And we do the same thing for the momentum after. With these two expressions, we can plug into our conservation of momentum equation. And if we do that, we get this expression here. Next, we know that momentum is equal to mass times velocity. So the momentum A is going to be equal to mass A times velocity A, and momentum B is going to be equal to mass B times velocity B. So we can use these definitions to represent the momentums like so. From here, we can identify that the velocity after for A and B are going to be the same. They're going to be equal to V2 because if we look at our diagram here, they travel together at the same velocity. So we can plug in V2 for both. And then from here, we can plug in our knowns. So we know the masses of both objects. The velocity A before is going to be equal to 2 meters per second. This is the velocity of mass A before the collision. And then VB before, this is going to be the negative 2 meters per second. This is the velocity of mass B before. So we can plug all these values in, and then we can start by first computing the term on the right. We can start by isolating for V2 by multiplying the top and bottom by V2. And then we can just simply add the masses together. We get 0.8 kilograms V2. Then we can compute the two terms on the left by computing the amplitudes in the units. And if we do that, we get this expression here. Then we can do a simple subtraction. From here, we can isolate for V2 by multiplying the top and bottom by 1 over 0.8 kilograms. We do a simple division and we get this for the final answer. So this is the final velocity of the masses. So important thing to note is that we can see that kinetic energy is not conserved because the kinetic energy before is going to be equal to the kinetic energy of A plus the kinetic energy of B. And if we plug in our known values, we end up getting 1.6 joules. And we can do the same thing for the kinetic energy after. It's going to be equal to the kinetic energy of mass A plus the kinetic energy of mass B after. And if we plug in our knowns, we get that the kinetic energy after is equal to 0.1 joules. So we can see that the kinetic energy before is greater than the kinetic energy after. And this can be seen by calculating the change in kinetic energy, which is negative 1.5 joules. And this means that the system loses 1.5 joules of kinetic energy from the collision. And this makes sense because the final velocity is much smaller than our initial velocities.